Professor Arindam Ghosh was awarded the Infosys Prize in Physical Sciences in 2020 for his work on light matter interaction with lead materials and his contribution to the global development of the field of two-dimensional materials, making him the first experimental condensed matter physicist to be awarded the Infosys Prize in Physical Sciences. Professor Ghosh, it has been nearly 2.5 decades in research. What do you see as your legacy in your field of work?
Right. Thank you, Ajay. Well, I would like to see that through our work, a new fundamental physical concept developed in our lab, through experiments that results in new devices and that can revolutionize certain key technologies. In the history of science, a conceptual breakthrough often results in new technologies, computers, for example, today. But there's always a time difference with it, and often done by different set of people also. We would like to see that we have taken a research happened in our group and impacted a technology radically and made a difference in the social life. So that's probably what would be my goal, I would say.
Absolutely. And we do believe that your work will be creating significant impact practically. In fact, we will be looking at the practical implications of your work soon. Professor Ghosh, you did your undergraduate from Calcutta University, master's and PhD from IISc, and then your postdoctoral research at Cambridge, UK, before coming back to IISc again in 2005. In this span of time, you have worked with many brilliant minds, your professors, colleagues, students. Can you tell us who or what inspires you?
Okay. So first of all, there are two parts of the question: who and what. So obviously, what inspires you is a certain practice, certain culture, scientific culture is what I mean, and who inspire me are those who follow those cultures. I would really go back all the way to my high school days, where I'm from a culture where theoretical physics is very strong, but not experimental physics. So I met Professor Manindranath Mitra during my high school days, who really showed the joy of doing experiments in my undergraduate days, actually. And then I came here to do PhD, my PhD supervisor, my postdoctoral supervisor in Cambridge. So we found that there are several people who looked at experiments in a very different way, and always told me that at the end of the day, the experiments are those which gives you the truth. And hence you should always look at this experimental physics. So that's what the cornerstone of my professional upbringing. And then what inspires you is another different question, and the question I would answer it as the challenge and the difficulty, and the greater the challenge, the higher is the reward and the satisfaction. So we are experimental physicists which make devices and which need infrastructures, which simply was not there when I came as a PhD student in IISc. I went to Cambridge for a postdoc and found that the infrastructure is. Even when I came back to India, I knew that we need infrastructure to do these problems, which the ideas that we had, but it would be an uphill task. So that was the challenge, and it's the challenge that inspires you. We went about doing it. Of course, there were great help from our colleagues. Still continues. It was slow and painstaking, but the difficulty in doing the job and the reward is the inspiring aspect that keeps us going.
Definitely. And that's exactly the trend we see looking at your education and career path thus far. a passion for challenging research. In more than 25 years in research, we want to know what drives you to come back to the same problem day after day.
Ajay, I would say it's the excitement and the joy to know that something that we have observed or discovered that no one else in the world knows yet. It can be very small, it can be as just one single data point on an experiment or a measurement that we are doing on a device that we recently fabricated. It doesn't have to be a massive discovery, I mean, it is um, just a new piece of information that the research gives you on a new idea that we are trying to verify or work out. So it's completely the excitement obtained through research that makes you excited to go get up in the morning and go to work. Of course, in addition to that, we interact with students, we interact with colleagues and exchange ideas with them. So that makes a very, very thrilling and exciting time that keeps us going.
I'm sure your students and colleagues would be so happy to hear this, the excitement in research that births from the exchange of ideas. We have a very hypothetical question. If we were to keep all that research away, what alternative career would you have considered?
Well, a cricketer, maybe, but that needs a separate set of skills. But otherwise, on a serious note, I used to love doing solving problems, and the more difficult the problems, I used to get more excited, and those were my favorites. So I was good at finding symmetries or patterns in difficult puzzles or problems. And I never really liked doing or being told what I should think about. So maybe a structured time-limited job would never be good for me. So I would say maybe I would have been investigative journalism or criminal investigator maybe, or maybe some form of data or financial analyst. I mean, where I deal with a lot of patterns and data. So yeah, I mean, I haven't really thought very carefully about what I would have done because I think I'm doing my first choice.
Judging by your investigations in physics, I believe the world missed out on a brilliant investigative journalist. But clearly, the scientific community has found a great asset in you. Talking about the scientific community, besides honoring outstanding research in the 6 categories, one of the main objectives of the Infosys Prize is to create role models for young researchers in the country. Professor Ghosh, what would be your message to aspiring researchers?
The most important point is to recognize that research must be driven by excitement and not by prospects of grades or recommendation letters or the jobs. You must choose a field of research that excites you the most, that makes you think about what will you do next, okay, in that field, and not by whether this field will give you a great job after you complete your master's or a PhD or a postdoc. Because if you're excited by the problem that you're doing and asking the right questions, then you are automatically going to end up doing a fantastic job. And that's extremely important, that we think, we find the beauty and the depth of the problem that we're working on, and which will naturally take you to the dream job. So most important problem that we find even as a researcher in India, elsewhere also, it's not completely untrue, that we often look at a research problem and find out, okay, this is a good field of research because it's going to give me a good job. But I think it's important to reverse the thinking process and say that, okay, is that field really exciting? Do I really like it? And do I have nice ideas that I could work on? And then simply dive into it. Not thinking about the finality of it. What finality will take care of itself. And I would say that this is the attitude that we should enter research with.
Thank you. We will go a little deeper into your specific area of research, and let me begin by asking, what got you interested in research into two-dimensional materials?
Okay, right. So it's, what got me interested. There are two reasons. One is, of course, my upbringing as a researcher. When I was during my postdoc, I got introduced into physics of two-dimensional systems, which means essentially when electrons and other kind of quantum systems are confined into just a sheet or two-dimensional planes. That's then when I came back to India for my starting my own laboratory, we just realized that there has been a discovery of graphene, which is a first two-dimensional material, and it was a natural interest for me. It was also a very new system where the properties are completely unique. It was totally different from anything that we had known earlier. The electrons in graphene behaves completely differently from the electrons that is there in semiconductors, of which our computers are made of. So naturally, there's a question that we had started asking that, okay, as a person who is already in the two-dimensional regime, whether we can work towards it. What's more important is that when I came back to India, then the infrastructure was still developing, and the two-dimensional material naturally gives you certain advantages in terms of infrastructural requirement. It doesn't require heavy foundries or very high, expensive equipments to get at least started. And that made me interested to getting into the research of two-dimensional material. Of course, as time went along, we just simply found that it's a gold mine, because we started with one material, and in next 2 or 3 years, or maybe 4 or 5 years, the number of materials started proliferating. There are new materials with the new properties have come up. So we realized that this is something which we should definitely invest in for a while. So I would say that would be the history of my entering into two-dimensional material field.
Thank you, Professor Ghosh. We said we would be coming back to the practicality, and here we are talking about your work in two-dimensional materials. Would you be able to tell us some potential practical applications of your work?
Sure. So that, as a whole, my work involves a specific class of materials, as you said, the two-dimensional materials, and make devices from it with certain properties that we have pre-designed. So, we can either make it a highly efficient converter of light into electricity, or some other, properties, for example, converting heat into electricity. So the practical application is never far away, because we believe, we can apply into new generation of optoelectronic sensors like cameras, where you can try to, install these devices as tiny detectors which can do nighttime imaging or imaging objects which are very far away. For example, in astronomy, you can image galaxies with these kind of extremely efficient. On the other side of it, you can have from these kind of geometries, invade energy into electricity. And hence, that could be a direct connection to the environment sustainability. But apart from that, what we are doing now is that we are taking this line of work, which is essentially 2D materials and molding 2D materials into different devices, into a completely uncharted territory. For example, these days we are trying to make smart memories with it. Memories which can not only store information, but also can manipulate or calculate with information. And one of these memories, or one of these directions is called neuromorphic devices, and which are devices that can mimic the functionality of the brain. We believe that these kind of two-dimensional materials can actually impact a very wide range of practical application. It's in the early stage, but it's something which several countries are already investing in to getting it from fundamental research to actual commercial product.
Thank you. You did mention imaging devices, photography in space, medicine, security. 10 years from now, how radically do you think advances in the field will change devices? Could you give us an example?
Right. So I can give you one example. So one of the example that we always take, because this is an emerging technology, is called the quantum technology. This quantum technology involves several aspects. For example, making a quantum computer, which is a next generation computing device, is one of the major goals. Communications is one of the aspects of where you take information and transfer it from one part of the world to another part, and which is impossible for someone else to hack into. So there are certain aspects of these emerging technologies that require devices with very different type of functionality, or properties. One of the example is single photon detectors, and in which you should be able to make up devices that can work, that can detect just one photon, which is really the basic unit of light and information. And we require devices, better and better devices, to make these kind of technologies come to fruition. One of the is metrology or sensing. Even in the case of GPS or earthquake predictions and so on and so forth, there are now requirements of new devices that coming up. Our work in 2D material and 2D material related devices are directed towards these next generation technology, where we believe the optoelectronics, we believe the thermoelectrics, the neuromorphic designs is one of the major directions in which one is talking about the quantum artificial intelligence and machine learning. So we hope that our work will actually make a radical difference to technologies of this sort.
Absolutely. And we're so certain it will. Professor Ghosh, working with researchers, we understand one of the most challenging parts about research would be making the people outside your field to understand your work. Even more, children. Professor Ghosh, we have an important question for you. How would you explain your research to a 10-year-old?
Now, that's the most difficult question that you just asked. Okay, maybe think of a camera on your mobile phone. I think that even the 10-year-old today knows very well about the cameras on a mobile phone. And what do you do? What does the camera do in the mobile phone? When it takes a photo, and then you store those photographs digitally, and you can then email it to them to your friends, or do whatever you can do, all sorts of modifications to the pictures, and those are fun things that you can always do. But what actually happens in photography is there is light which comes on and hits a material, and light then produces charge or electricity. Okay, and better the camera, the larger the charge from a small amount of light. As a result, what you can do is that you can image photographs even when it is dark, or even if your friend is standing very far away. So there are now continuous requirement of better and better converters of light or photons into electricity, which can be stored. Our work is exactly towards this. Our work is taking all these information that is hidden in light, hidden in heat, hidden in charge, and converting in them into electricity that can be stored, that can be used later, that can be modified, and do this in such a high efficiency that no one has done before. As a result, you can probably take pictures, even if you cannot see anything, but you can still take pictures and get information about what is there in front of you. And as I said, it's a dark time. Even if it's night, you can take pictures. For example, this could be useful in strategic sectors, in army, and so on and so forth. And even when, as I said, your friend is very, very far away. So maybe that's the best way of explaining our work. To get to this particular point, we have been able to design a completely new kind of materials, to completely new, which is built on different than existing materials, and hence we are able to do things which no one could do before.
You definitely have simplified it. I'm sure that was difficult. Professor Ghosh, I wanted to ask you a reflective question. Can you tell us how the Infosys Prize has impacted you?
Well, Ajay, as they say, it's always the journey rather than the destination. The destination is not very well defined at all for us because we never know where science will take us. But there are points of the journey where the recognition of the peers do help us in ensuring and confirming that the route that we are taking is the right one. It's something which gives us confidence, and it gives us I would say the vision that not maybe today, tomorrow, maybe day after tomorrow, we would like to make a difference. So what Infosys Prize probably has done, as far as my personal viewpoint is concerned, it has made me more confident about the science that we are doing. It also made a lot of difference to the students, who not just those who are working with me, but in general those who are associated with me through my departmental colleagues or through those whom I interact through collaboration. So they all have a certain degree of confidence that they are working on something that can really make a difference. So I would say that is the first and the foremost impact that Infosys Prize has taken. The vigor in which we have worked, we always work with a lot of passion, with a lot of enthusiasm, and we are now more confident in executing our tasks as we come to our work every day.
This is so encouraging to hear. Thank you so much, Professor Ghosh. It's truly been a joy talking to you and hearing not just about your work and research, but your views and approach to it. Thank you.